right, so looking at our schedule, we have polygon sum theorems, check. Proving and understanding properties of parallelograms, check. Your quizzes, I have about half of them graded. So my plan is to give them back to you when I see you next week. So far, so good. We did a real quick lesson on rhombuses, rectangles, squares, and trapezoids and kites, and we're going to continue that today, along with talking about areas, quadrilaterals. I also want to make sure I give your triangle Unit 6 trig tests back. I meant to do that 2 days ago. The grades are in, sis, so we want to make sure we get that straightened away before you walk out the door. And then, believe it or not, already we're looking at another review and test. So here we are today at the end of the third quarter. Lots of questions about what is or what is not on the third quarter. And basically, it doesn't matter. Because of our rolling grade book, we just keep going with the grades. So my goal is to get the quizzes graded and hand them back to you here. But I'm going to put them in as third quarter grades, so they'll be in the calculations and the progress reports. Keep in mind, as we move on, our formative grade category is shrinking down to where it's supposed to be, only at 30% of your grade. And because it's one big pot, every quiz we put in matters less. Do you understand what I'm saying by that? Put your pencil down and listen to me so I know you're paying attention, because it's important for you to know about your grades. That formative pot now has all the quizzes from units 1, 2, 3, 4, 5, and 6, and now unit 7, all in it. So they all go in as out of 100%, out of 100. So they're all equally weighted, so they all just get mashed into that big pot together. All right, our summatives are now what we really need to keep our eye on the prize, because our summatives, each time we add a summative test in, more of that 70% is complete. So we have the units 1, 2, 3, 4, 5, and 6 are now in that. So when we look at each of those grades, we're now at the final point where the summatives are weighing more than the formatives. So those are the ones that you really want to make sure you knock it out of the park of. It's going to be frustrating for you because your grade, if you want to change your grade and your percent, you're going to have to really, it's like you're pulling up that whole total. And it's important to understand how each of those things work. So thank you. Some of the kids are frustrated when they do better on a quiz because they're like, oh, I did great on that and it didn't improve my grade. It's going to take a lot to get those grades to move because of the rolling grade book. So think about those percentages and weights and etc. When I give you back your Unit 6 tests, we're going to have this retake date here, going to be that Thursday before spring break. So it is a quicker turnaround, but I don't want that dragging on, especially since you're going to be getting a Unit 7 test score back. That's that weird situation where our tests and our retakes are going to lap each other. That's a lot on somebody's brain if they're trying to take every test twice and do those retakes. In one of my other classes, I handed back a Unit 6 test and the kid did well on it, and he looked at his partner and he goes, see, the 5 weeks of focus pay off. And it totally made my day. Because here we are at the end. Remember when we talked about it 5 weeks ago, thinking, oh my gosh, that felt so far away. You're busy, you've got stuff going on. You got outside school activities, you've got other classes ramping it up. So if you've been working hard, you're probably tired, but it's going to feel good when those grades pay off. Okay, diving right in to today's lesson. Go ahead and take your packets out and let's have a conversation about where do we want to start? let's have a conversation about, here we go, all of these lovely shapes. So when we went ahead and looked at all of these shapes that you had, and you're like, man, I don't have my shapes anymore. That's okay, I got them here for you. And we'll talk about each of these things. And I don't want you frantically copying down the letters, because at the end of the day, the letters don't matter. What I want you to make sure you have correct is, after you read all of these descriptions on the far left, having this name on the right. And I don't know how far you and your partners got in your sorts, but it's important that you understand this conversation between all of these descriptions and recognizing what our most specific name is. Yesterday I gave this sort to my 7th period, and the one kid's like, they're all polygons. And you started to write polygon, 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 polygon. I'm like, stop. We're not going to list polygon, 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 polygon. Can you come up with something more specific? So he takes a look at all the shapes, and he's like, oh, they're quadrilaterals. So he erases polygons and starts writing quadrilateral, 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 quadrilateral. I'm like, stop. Can you find something more specific? And that's when he got what we were going for in this conversation. If I have a shape where I have 4 right angles, that polygon, that quadrilateral, that parallelogram is something even more special because it's equiangular. And because I know it's equiangular, I can go ahead and call it a rectangle. So when we ask you these questions in this unit, suddenly what you think you've understood about squares and rectangles and are going to suddenly get all twisted up in your brain, because you're going to have to keep track whether we're talking about all the shapes that match that category or the most specific shape that matches that category. If I ask you for a shape that has 4 right angles, yes, it's polygon, yes, it's quadrilateral, yes, it's parallelogram, yes, it's a rectangle. Are we asking for our most specific name or all of the names? So go ahead and look at exactly one set of parallel sides. If I have exactly one set of parallel sides, I'm talking about my trapezoids. Go ahead, Molly, what's up?
The number 1 can also be like square.
We're not going to say square because you want to find the most specific shape that has that all the time. And you would not call this shape a square. So it's got to be a category that fits all of them. So if I talk about all the shapes that have the right-hand sides, this guy lost his, they're not joined. That'll be a problem. Let's see if it happens again, and then we can have more of an opportunity. All right, so Molly asked a great question I want to make sure we listen to. She's like, well, why can't I describe them as squares? Thank you, Marisol. Marisol, grab that one more. Why can't I describe them as squares? And the answer, because if I put all of these shapes that have right angles in this group up here, not all of them are squares. So we want to make sure that we come up with the most specific name that fits every shape in that category. Does that make sense, Molly? Awesome. That was a great question. Good place for you. One set of parallel sides, those are our trapezoids. Now notice when I was with you 2 days ago, I went ahead and I highlighted each of these conversations that are part of our 6 about parallelograms. Those features having 2 pairs of opposite sides congruent, 2 pairs of opposite sides parallel, having opposite angles congruent, and diagonals that bisect. When I put all of those shapes and conversations into one category, check it out, I end up with all of my parallelograms. And it's interesting to look at and note what ends up happening when I look at what I don't have. Here's my trapezoids. Here's my darts. Aren't the kites super fun?
Yeah.
How cool is it that they named it something that it looks like? They're like, thank you for being reasonable. And then this guy, he's like the one that nothing fits, right? He's just a plain old quadrilateral. Where did you put I? Having 4 sides.
No congruent.
There they are.
No congruent on.
And having no congruent sides. We're just going to call that a quadrilateral.
And convex.
Yeah, convex.
And convex. Because these are our concave shapes, our darts. Whether we call this an isosceles dart, it has 2 sides. And that isosceles dart is crazy. You can think of it like a kite. Because I have 2 sets of consecutive congruent sides. When you're looking at your grouping. So if you didn't get a chance to finish your sort, I'm not surprised because we're kind of crunched on time. So what I want you to do is basically, you can kind of, unless you saved your shapes, this middle column doesn't become a meaningful conversation to you. But what's cool is maybe you could even fold your paper over and do like a little tucky thing. I'm going to borrow the pages for just a second. If she folds her paper over, it becomes a pretty decent study. See how I made a little accordion fold? It becomes a pretty decent study guide if you want to review. And then putting this like this makes it so you can quiz yourself. So quizzing yourself back and forth, or reviewing, or you're like, stop messing with my packet. You just bent my packet. Don't do it. But that middle column, once you stop playing with the shapes, is not relevant. But I do want you to have all the correct names down. Are we good? Thumbs up if we're ready to move on.
Can you just scroll to 15?
Scroll to 15. There's one more. Here we go. What? Those are squares. 4 congruent sides and 4 congruent angles. Any questions on any of these you want to talk about? Awesome. In our next conversations, we went ahead and we talked about, and what I want to make sure is you understand, and I don't think with your class we included this conversation about parallelograms at the top of the page, did we? And what I want you to understand is every single thing about parallelograms is true for rhombuses and rectangles. Everything that's true for rhombuses and rectangles is true for squares. So this whole trickle down is what is involved in this, circle here. So when I talk about this circle here, I have my parallelograms first. And then in each of these, whether I have my rhombus or I have my rectangle, and I know that those two things together gives me my square. Seeing how all of these things funnel down and lead to the one next thing in that Venn diagram is a pretty interesting visual. When my daughter was in preschool, she came home and I got in the car. I went to pick her up. She gets in the car. I'm like, how's your day, Caroline? She goes, terrible. I'm like, what happened? She goes, I have a stupid teacher. What happened? Tell me what's going on. She says, my teacher says we live in Virginia. I said, we do live in Virginia. She goes, you said we lived in Herndon. I'm like, well, we do. She's like, well, which is it? Do we live in Virginia or do we live in Herndon? I'm like, well, maybe we live in both. Because Herndon is a special part of Virginia. She goes, well, does everybody that lives in Virginia live in Herndon? Only people live in Herndon. There's lots of little towns. So explaining the difference between Herndon, Virginia, the United States was an interesting conversation. That blew her mind. She couldn't understand it. So I'm like, you have to go back tomorrow and apologize to your teacher, because I'm pretty sure if you thought she was stupid, she knew you thought she was stupid. And she goes, yeah, I told her. So I was like, okay, let's sit down and write a note of apology to your teacher. But understanding these nested diagrams is important, and if it helps you keep it straight, go ahead and if you want to think about this as Herndon High School, because people from Reston and Virginia come to Herndon High School, and everybody lives in, if you want to say Fairfax County, if you want to say it even bigger, Virginia, even bigger, United States of America, even bigger, North America, even bigger, planet Earth, because you can continue zooming out or zooming in if you wanted to get more and more and more and more specific. These nested diagrams show that specificity. Say it again. But it ends in an itty. Specificity. Say it. That. All right. If you filled in these conversations when we were talking about our flow chart and our flow diagram, I told you to put parallelograms here, and I told you that we could put a rhombus here. I still can't say that word. And rectangles here. And then recognizing that, of course, our square is here. So then our conversation goes to these other friends. These three other conversations, trapezoids, kites, and darts. And trapezoids are, I think they are the most underestimated and devalued shape in the whole conversation. Because trapezoids have three different subsets, whether I have a regular trapezoid, where it's just exactly one set of parallel sides, whether I have a right trapezoid, where I have a right angle involved in there, or whether I have an isosceles trapezoid, where I have two congruent sides and congruent base angles. So if you wanted to represent your trapezoids with all those cool conversations, if you wanted to talk about them, and then find room to write your three different kinds of trapezoids, that's up to you. As far as they're concerned, recognizing that a trapezoid is a special kind of quadrilateral. Then you're good to go. When we talk about kites, that's our conversation about our two consecutive sides that are congruent, perpendicular diagonals. And I often like to think about, like, if this used to be here and I put my mouse here and clicked and drug it, I just pulled and stretched out one part of that. And then, of course, our darts are our concave quadrilaterals, and we can have two conversations with our darts, whether we talk about it being isosceles. If I have two pairs of consecutive congruent sides. Are we okay with all of that? All right. So I asked you for homework to go ahead and do a little who am I with our list here. I'm a parallelogram with congruent diagonals. So close your eyes right now. I know two shapes that have congruent diagonals. I know a rectangle has congruent diagonals, and an isosceles trapezoid has congruent diagonals. Two of my side lengths are 4 centimeters and 10 centimeters. What Turn to your partner. Actually, what I want you to do is these in groups of 4s. So I would like Barry to turn and join this group. You two join and talk. You two join here and talk. You two join here and talk. You two join here and talk. You guys talk. You guys talk. You guys talk. Everybody talk through each of them and compare your answers. Marcus, say go. How come this first one cannot be an isosceles trapezoid? Doesn't an isosceles trapezoid have congruent diagonals? It can have sides of 4 centimeters and 10 centimeters. If the 4 centimeters are like this, right? Go ahead.
It's because it's a parallelogram.
Yeah, it says I'm a parallelogram. Trapezoids are out of the picture. All right, ready? Number 2. It is a right. Thumbs up if you agree. All right. Number 3 is a
Trapezoid. I told you.
is a trapezoid. Any questions on any of these? Let me know, and I'll be glad to tell you how number 4 is a rhombus. Number 5 is a parallelogram.
It's a parallelogram. None of it's not right.
Number 6 is a rhombus. And number 7, square. Number 8, here's our isosceles trapezoid. Being able to tease out each of these conversations, anybody need help with any of them? Anybody want to talk about any of them?
How do you know it's an isosceles trapezoid?
So the diagonals are congruent.
Yeah, I got rhombus.
So if it's a rhombus, it's not going to have congruent diagonals.
Oh, it doesn't?
No, think about this. Look at this. Here's my fun coat hook. All of these are rhombuses. See how I have a short and a long diagonal?
Yeah.
If it's a square and a rectangle, then it has congruent diagonals. But it's not going to be a square and rectangle with those measures of 65. Right?
Yeah.
Lots of thinking here. Lots of if-thens. Lots of if this is true, then that's true. But wait a minute, what about this? And being able to look at those categories inside out and upside down. All right, are you ready for this? Your sketches for parallelogram, rectangle, rhombus, square, kite, and trapezoid should try to show those features that'll help you figure them out. Both pairs of opposite sides are parallel is a conversation for parallelograms and anything that is a parallelogram. Exactly one pair of opposite sides are congruent. That is only true for our trapezoids. All sides congruent. That's only true for our rhombuses and squares. Both pairs of opposite angles congruent. We go back again to that's one of our definitions of a parallelogram. Exactly one pair of opposite angles are congruent. That is our kite. When we talk about all angles congruent, that's only going to happen with our square and our rectangle. Right? Our square and our rectangle. Our next conversation again is part of the definition of a parallelogram. So my diagonals are congruent. If I have a rectangle, if I have a square, and I'm going to go ahead and say if it's an isosceles, ISOSCELES, trapezoid. Took me a minute to spell isosceles. Only if it's an isosceles trapezoid. Diagonals are perpendicular. That's going to be in our square and our rhombus. Diagonals bisecting each other, that's another parallelogram feature. Consecutive angles supplementary, that's another parallelogram feature. And 4 right angles is our rectangle and our square. So it's tricky when we're asked to list some of the features, all the features, most specific features, etc. And that ends up showing up particularly when we talk about your warm-up.
Wait, I'm confused about a couple in the last one.
Go ahead.
I thought, so when it says all sides are congruent, I thought it could also be a rectangle because squares are rectangles, right?
Right, but does every rectangle have 4 congruent sides?
And then also, for the bottom, I thought all of the shapes have a second diagonal, do they not?
The only diagonals that bisect are going to be parallelograms. Because the trapezoids don't bisect, one part of the diagonal where it crisscrosses is going to be shorter than the other.
Oh.
And then for a kite, one end of the diagonal is going to be longer than the other. So that doesn't work out. Go ahead, Farah.
Our kite diagonal is not perpendicular.
Kite diagonals are perpendicular. Did I not include that? Kite diagonals perpendicular. Farah, you can put Smarty up. Oh shoot. Is this the kite? Yeah. Go ahead.
Do rectangles have perpendicular diagonals?
No. Only when they're squares. But not all rectangles do. If you're ever in doubt, draw yourself an exaggerated version of the shape. So for example, if I'm looking at my rectangle, I'm going to draw a rectangle that's a very exaggerated version of that. Let me try to make it straighter. I'm going to draw myself a very exaggerated version of that shape. Not much better. Because when I go ahead and do my diagonals, there's no way they're going to be perpendicular, right? So anytime that you're drawing something to see about it, like for example, my kite, I'm going to go ahead and draw an exaggerated version. And the kite is kind of crazy because we've got some things are true and some things are not true. So this diagonal is bisected, but this one's not. These opposite angles are congruent, but these ones aren't. So if you're testing out a shape, draw a super slanty rhombus, and you'll see that the diagonals are not congruent. Draw a super slanty parallelogram. Draw a trapezoid that's completely wacky, because that'll help you see those features, because if they're features that are true, they will always be true. Make sense? All right. So now I want you to dive into your warm-up, and I want you to come over here. Complete the chart using this format. And this is straight from Delta Math, if you saw that assignment. This quadrilateral is most specifically a blank because blank. So I'm not going to ask you to write this sentence, but I want you with your partner to say, this quadrilateral is most specifically a blank, and you're going to fill in the list of what it is most specifically in there. And then your word because, remember this is our word of the year, because. And then that's what I want you to say. So turn to your partner and fill in the top of this chart and move on to the bottom when you finish. Go. Number 1, say it out loud. This quadrilateral is most specifically a trapezoid because
One set of parallel lines.
it has exactly one set of parallel lines. And those angles, those angle measures validate the fact that we have 2 sets of consecutive interior angles that are supplementary, but notice the opposite angles are not congruent. So don't be afraid to sketch something that makes sense to what that diagram shows you. All right, number 2, this quadrilateral is most specifically a parallelogram because,
Opposite
Yeah.
sides are congruent.
so we can say that opposite angles are congruent. If you want to instead, you can say consecutive interior angles are supplementary. Those angle conversations definitely work together. All right, our third shape. This quadrilateral is most specifically a quadrilateral. How come?
Because it has 4 sides.
It has 4 sides. That's all we know. You could say it looks like maybe a trapezoid. You could say, but unless you're given information, we're not going to go with that. Wow, we got more information than we know what to do with on this one. This trapezoid is most specifically a, yeah, we're definitely going to go with rhombus. And they gave us a couple clues. Do you see how these diagonals are both bisected? But see how they used a different letter, a different variable for them? But I love that. They showed us our bisected angles. They showed us our bisected diagonals, but are different. They didn't show us perpendicular diagonals. That would have helped out, but we didn't need it. And they could have also shown us 4 congruent sides, but we didn't need it. Having these bisected diagonals proves it's a parallelogram, but it's these bisected angles that prove that it's a rhombus. All right, coming down to the second half. Choose all answers that describe the polygon if all of these things are true. So there's absolutely no way, well, I shouldn't say that because maybe some of you can, but let's go ahead and draw a sketch so we can see what's true for quadrilateral OPQR. A reminder, when we name polygons, it's consecutive order. It's ring around the rosy. So make sure that you have OPQR named appropriately. You can start on any vertex and go in any order, but one of the biggest mistakes you'll make is here switching Q and R. So make sure you get that in the right order. All right, if OP is 20, let's do this. OP is 20 and PQ is 40. All right, already I know it's not a rhombus and it's not a square. QR is 20 and RO is 40, so at least I know it's a parallelogram, it's quadrilateral. O and Q are congruent, doesn't change my story. P and R are congruent, doesn't change my story. OP is parallel to QR, doesn't change my story, and PQ is parallel to RO. None of that changes my story. Go ahead, Caroline.
Wouldn't it be a rectangle?
They didn't tell me anything about the angles. Because O and Q are parallel, and P and R are parallel, but there's nothing that would keep me from drawing this shape like this. Aren't my opposite sides congruent? Now, if they had told me that angles O and P were congruent, then I'd be in business. Because then I'd know they were all 90 degrees. But there's nothing to prevent me from drawing that shape like that. So we're going to go with it's a parallelogram and a quadrilateral. And this is snipped from MathSpace, and it drives me nuts. Because I feel like we should start with quadrilateral and then go to parallelogram. I don't know why they do that. All right, let's try our next one. Choose all answers that describe A, B, C, D. So all of my angles are congruent. Now I've got rectangle, Caroline. All my angles are congruent. It's a quadrilateral. It's a parallelogram, and it's definitely a rectangle. No, yes. But my diagonals are perpendicular.
Square.
And a rhombus. right? So if I drew this one, as soon as I see all my angles are congruent, I've got these all equal 90, but as soon as they tell me that my diagonals are congruent, I know that this side length is actually here, because that's the only way that I get congruent diagonals, is if all of my sides are the same. All right, let's go to our next one. Choose all answers that describe polygon D, E, F, G. DE is congruent to FG, all right? So when I go to look at, I'll just draw this and see how we go. If I have D and E and F and G, because they said that DE is congruent to FG, got it? EF is congruent to GD, got it? Measure of angle D and E and F and G are all the same, right? Which means yes, it's a quadrilateral, yes, it's parallelogram, yes, it's a rectangle. Am I done?
Yes.
Not a square because it didn't tell me that. It said opposite sides are congruent, but it didn't say all the sides are congruent. Yeah.
If it puts the angles as like equal to instead of congruent, then it's always going to be like 90 degrees.
Yes. So this is two ways that we can talk about our angles. Molly asks a great question. This is when I'm talking about my numeric measure, and this is where I'm talking about my angles being congruent. They will both tell you, if I know that some of the angles on the quadrilateral is 360 degrees, those two sentences say the same thing. One is talking about the angles, one is talking about the measures. Okay? All right, last one. Choose all answers that describe K, L, M, N. Okay, so I know all my sides are congruent. K, L, M, N, M, N. Diagonals have equal length. So if my sides are all the same, I know at least I have a what? I have a quadrilateral, 4 sides, I have a parallelogram, and I have a rhombus, right? Once they tell me, let's talk about K, L, M, and N. Once they tell me that these diagonals have equal length, I know what happens. Check it out. See all these little rhombuses? Are their diagonals the same?
No.
What happens when I reach the point where they are the same? Square. Right? If it's a square, what else is it? If it's a square, it's a rectangle. Also, not a trapezoid. We good? All right. Today's lesson. One of my truly favorite lessons to teach, because this is a life skill you're going to want from now on. If you notice on the back of your warm-up, I gave you a grid, because if the grid in your notes is not big enough, feel free to draw big and experiment on your own. That's your paper to play with. So if you're one of my friends that has all kinds of colored pens and pencils and likes to draw and sketch, here we go. The word area comes from an array. When we talk about the area of a figure, we talk about the amount of space it takes up. So anytime we talk about an array, we are arranging things in a way that I can count them and account for them in a faster way. For example, if I want to know how many magnets does Mrs. Glazier have, if I have them all arranged in this nice little array, you look at this and what do you see? 9. 9. Because you see 3 by 3, and you learned way back in the 3rd grade that 3 sets of 3, 3, 6, 9 is equal to 9. You don't do 3, 6, 9 in your head anymore because you've memorized that, and that's a rote memory thing that just comes out of you. 9. Caroline didn't even think of it. She went 9. You got 9 scores. When I arrange them in an array, that makes it easier for her to tell how many we have. If my magnets are not in an array, what do you have to do?
Count them individually.
1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, 9. Same thing validates. When we teach elementary kids about repeated addition, we arrange things in nice little blocks. We say to the kids, how many is that? And the kid goes 1, 2, 3. We know a kid is ready for multiplication when they do something called counting on. If you ask a kindergartner, okay, how much is that? A kindergartner is going to go back here and go 1, 2, 3, 4, 5, 6. A second or third grader is going to go 4, 5, 6. It's called counting on. So they'll remember their 3, and then they'll know that, oh, we keep going on to 6. If you ask a kindergartner how much this is, they'll come back to here. 1, 2, 3, 4, 5, 6, 7, 8, 9. You ask a kid that's ready to learn multiplication, he'll remember that 2 groups of 3 was 6, and he'll go, oh, 7, 8, 9. So as little kids' brains develop and become stronger and more capable of doing this, we introduce those levels of math, and they learn that this is 3, this is 3, this is 3. 1 group of 3 is 3, 2 groups of 3 is 6, 3 groups of 3 is 9. By the time you're in high school, being as brilliant as you are, you're like, it's 9. Because you do that math automatically in your head. But it's cool when you look at how kids learn math and you go back and pick it apart and look at, if you try to teach a kindergartner 3 times 3, he won't understand it because he doesn't understand this concept of counting on. So we gotta teach it in steps. It's kind of cool. People cared a lot about area because way back before we had any organized mathematics, they had to pay tax on how much land they owned. So if I wanted to know this two-dimensional representation of this land, I needed to know its dimensions. If I look at an array of 5 times 3, you know right away that's 15. But organizing those 3 groups of 5 or 5 groups of 3 is how we end up getting an area. Finding the area of our rectangle is the most basic conversation. Area is length times width. Got it. How many groups and how many rows do you have? 3 groups of 3, 3 groups of 5. We could do that repeated addition that gives us multiplication. If I have a square, then that means that my sides of my square are going to be the same. So instead of having a length times a width, I can just say that that's side squared. If you don't have enough bandwidth to remember those 2 formulas, it's okay. Just remember the one. Length times width will get you every time. What's super cool is from this one formula, we can get all of the other area formulas of the quadrilaterals that we are studying, and we threw in one triangle just for good measure. I know that the area of this rectangle is my length times my width. I know that to be true. But what's interesting, if you remember when we built your trapezoid or your rectangles, remember how they all started off as this. You started off with a rectangle. This rectangle has an area of length times width. The minute I turn it into a parallelogram by sliding this over, that area is conserved. This still has the same area. And if you look at it, it still has the same base. This base is the sum of these 2 pieces, this guy plus this guy. When I slide him over here, it's still this guy plus this guy. You okay with that? The height of this rectangle is still this. When I slide this piece over, the height of my parallelogram hasn't changed. So having this parallelogram made from this rectangle helps us see that if I want to know the area of this parallelogram, all I need to know is its height times its base. So its height times its base is going to give me that formula, because I can recognize that that parallelogram is just a tilted version of that rectangle that it was formed from. The true formula that you only have to remember is base times height. This base times this height, because I recognize that rectangle came from, or that parallelogram came from that rectangle. Did you know that every single triangle is 1/2 of a rectangle? So if I look at this triangle, I can see that it is 1/2 of that rectangle that's constructed around it. So guess what I can come back to? The area of a triangle is always base times the height, but it's only going to be 1/2 of that total space. So if I build a triangle, if I build a rectangle around a triangle, it doesn't matter what the triangle looks like, it's 1/2 of that base times that height. You can play with your graph paper and draw any triangle that you want, draw the rectangle around it, and its area is going to be 1/2 of that rectangle. Whether you draw a right triangle, a scalene triangle, an isosceles triangle, whatever triangle you draw, the rectangle around it is going to be double the area of that rectangle. All right, we already talked about this guy because we still have our base times our height. If you want to call that side squared, you can, because they're the same. All of those shapes are so 5th grade. We've had them before. Here are the cool ones. Are you ready? If I have a rhombus, I know a rhombus is a parallelogram, and I know I can do base times height for a rhombus. No problem. But something pretty cool is also true about a rhombus. Because I know that my diagonals are perpendicular, I can think about those diagonals as a base and a height. So you can think about this diagonal as this side length. You can think about this diagonal and that side length. So what you can see is that this side length and this side length form a box around the rhombus. So I like to tease my kids and say, okay, for your birthday, I bought you a rhombus and I'm going to wrap it. I'm going to wrap it up in a box. The dimensions of that box have to be equal to the base and the height, but it's way too big of a box, so I'm going to have to fill it with tissue paper because the rhombus only covers half of that. So my area is 1/2 of that base times that height. That base times height is the box I can draw around the rhombus, but the rhombus only takes up half of the box. You loved your rhombus that I gave you for your birthday last year, but this year you want something different. So, secret time, I'm buying you a kite. That kite, when I go to wrap it up in a box, my box is going to need to be this wide. And when I wrap my kite up in a box, my box is going to need to be this long. So when I go to buy my box to wrap up my kite for you, I'm going to have to buy a box that has this base times this height. But keep in mind, I'm going to have to fill it with tissue paper because that box is twice as big as that kite. 1/2 base times height is the area of a kite, and that base and height are the lengths of my diagonals. So we've had all kinds of great conversations about the importance of these diagonals. The height of a kite and the width of a kite, we can call base and height. So their areas are going to be half of that space of the box that they take up. And again, the graph paper you have on the back of your warm-up, if you feel like drawing some kites, drawing some rhombuses, and wrapping them up in boxes, it's kind of cool. So my length times width comes into my base times height, and notice I'm going to use base times height and thinking about what's 1/2 and what values are the same. My trapezoids are my favorite. Are you ready for the trapezoids? 2 different conversations about trapezoids. And I'm going to write the trapezoid formula over here. So the area of a trapezoid is going to be equal to 1/2 times the height times the sum of the 2 bases. The sooner you commit this to memory, the happier you'll be, especially when you reach calculus and you have to do all kinds of conversations with trapezoids. Sometimes we like to instead write this as my height times the average of the bases. Sometimes we call it half the height times the sum of the bases. Those 3 things are being multiplied together, 1/2 height and the sum of the bases, so whatever order you do it in, nobody cares. Here's why it works. If I take my trapezoid and I take half of the height, so if I have my height here, do you see if I have base 1 here and base 2 here, what I'm going to do here, and this is kind of cool, is I'm going to take this half of that piece there. Maybe I'll do it in a darker color. This darker purple maybe. I'm going to take that half of that and I'm going to flip it or rotate it around and bring it down here. Do you see how I just made a rectangle? What is the height of that rectangle? 2. It's half of the height. Do you see now here? I divided my trapezoid into 2. So here is 1/2 of the height as a measurement up and down. Let's talk about how long that triangle is. Here's base 2, but what is this length here? So half of the height times the sum of the bases. You can do that with any trapezoid. Find the middle of it. Find the middle of it. Take the trapezoid on top. Rotate it around that point. And you'll notice that my height here is cut in half. Here's half of the height. And if this is base 1 and this is base 2, half of the height times the sum of the bases. Draw any trapezoid you want on that grid, and you can chop off the top of it, flip it around, and it can make a parallelogram, or it can make a rectangle with that half of the height times the sum of the bases. Now, what kind of a learner are you? I'm a concept-based learner. If I understand conceptually what the formulas are, I understand about the kite being half of the length times the width. I understand about the rhombus being half of the length times the width. I understand the triangle being half. Each of these are half of that box I drew around it, and when I go to do my area formulas, that's what I see in my head. I remember this trapezoid being flipped around half of the height times the sum of the bases. I got it in my head. Maybe you are a formula memorizer. Maybe you're like, I don't need gimmicks. Just tell me what it is. All right, the area of a parallelogram is base times height. The area of a triangle is 1/2 of the base times the height. Turn your page. Area of the trapezoid, half of the height times the sum of the bases. Area of a rhombus and a kite, 1/2 the product times the diagonals. Off you go. Yes.
Wait, isn't the area of the rhombus and the kite formula the same as the triangle? Because it's just 1/2 base times.
The area of the, yes. 1/2 base times height. 1/2 base times height. But we're going to call it the product of the diagonals because the diagonals are the base times the height.
Okay.
Make sense? All right. So your homework is going to be to practice doing these, and I would like you to learn to write an area formula in a certain way so you get credit for it. When I hand back your Unit 6 test, a couple of you will see you put down an answer that was wrong, so you lost 2 points. The person sitting next to you put an answer down that was wrong, but they only lost 1 point. What the heck? If somebody shows their work and a trig ratio that was correct, but they had clumsy thumbsies, they got 1 out of 2 points. When we do area, we're always going to start off with our formula and what we plug in. When I want to find the area of this shape, we've got all different things that are inside that we need to try to figure out. This 9 is the measurement of that height. Here I have 20, which means that we're going to go ahead and say that this value here is also going to be 20. Here's our 20, and we're going to let AD also equal 20. So if I want to find the area of that whole parallelogram, I can say that my area is equal to my base times my height. So my area is equal to 9 times 20. So my area is equal to 180. I don't see any units, so I'm going to say that 180 square units. We measure area with how many little squares fit inside that space. Now, if you wanted to, you could break this shape up into the trapezoid and the triangle, but I'm okay with calling that whole area that parallelogram. Now I need to know this length here because this is the height to this side of the triangle. So little Pythagoras will help me out. 15 squared plus my side squared is going to be equal to 20 squared. So 215, what's 15 squared? Oops. 225. 225 plus a squared is equal to 400. So, just checking, 20 squared, yep, minus 225, 175. So my a is going to equal to the square root of 175. How many 175 divided by 25? 7. So we're going to instead call that A. A is equal to 5 roots of 7. So I know this side is 5 times the square root of 7. So for my second one, I know that my area of that triangle is 1/2 times my base times my height. So my area is equal to 1/2 times 15 times 5 roots of 7. So my area of my triangle is going to be equal to 1/2 of 15 times 5. So 15 times 5 is 75. 75 divided by 2, 37.5 roots of 5. When I want to know my total area, it's going to be the sum of these two things added together plus 180, 217.5 roots of 5 units squared. Yes.
Why is it roots of 5 instead of 7?
Oh, darn it. Thank you, Grace. I got it right up here, but wrong down here. You can put a Smarty up. And then here too. Marvelous. Thank you. The long and short of this is when you are figuring out area, this is called a composite figure. And you are allowed to figure out the area of any piece of the composite figure because area is conserved in its pieces and parts. The same as how I showed you the area of the rectangle is the same as the area of a parallelogram. If I took the time to calculate the area of this trapezoid and added it to this triangle, it would be the same as the area of this rectangle, and it would be the same as the area of this parallelogram. Area in composite figures is conserved. I saw a question. Go.
So I've been following along, but I'm just kind of confused because isn't A, B, C, D the just the parallelogram?
So all I needed was the parallelogram.
Yeah, because that
that's like
size is
your-
unlinked.
Yeah.
Step 1, read your directions. Do you think that they didn't want us to know it was a parallelogram?
Probably.
Do you think that they wanted us to find the triangle and the trapezoid separate?
Well, there's a big track.
Yeah. Because
I just like 20 times
do all
But it was so fun. You see all the fun we have with this math? Carl is so excited. Hey, one thing I want to make sure that you understand when we talk about this next problem, the height corresponding to a 15 centimeter base, when you talk about triangles, trapezoids, and parallelograms, it matters which height you're looking at. So think about this in one respect, and I want you to draw some sketches with me. If I have a parallelogram and it tells me the height to that side, if I take this same parallelogram and spin it so that something else is its base, I might have a different height. So if I'm talking about this base 1, this becomes this base 2. So when I'm talking about my parallelograms, if they talk about the height to that base, that determines which one you're doing. So our areas are going to be the same, but I want you to think about the fact that this triangle completes this triangle here is what completes that. So if I talk about this rectangle here, it's this rectangle with this base and this height. If I'm talking about this conversation, this triangle makes that rectangle. So we want to make sure that you understand what we're doing when they talk about the height corresponding to that base. Go ahead.
Are we ever gonna do anything with darts?
With the darts, we're not going to figure out their area unless we figure out if we're given a lot of information where we can piece it together or subtract the part that's missing. Go ahead. Oh. Do you understand this conversation about, and what's interesting is if I drew both of these rectangles here, let's say I talk about this rectangle here, the height of one is the base of the other. So if I took this rectangle and spun it, see how that matches up? So understanding what we're talking about with this conversation here, where it says the height corresponding to a 15 centimeter base, and then they ask you to find the height corresponding to the other base. In number 3, we're talking about what 2 methods can be used to find the area of the rhombus. If I have this rhombus, this base that's 20 with this height of 19.2 is going to give you its area, base times height. So if I wanted to do the fact that this area is equal to that base times that height, I could absolutely do that. Instead, if I wanted to look at the diagonals and say my area is equal to 1/2 of the product of each of those diagonals, either way, I'm going to get the same answer. Make sense? All right, for your homework tonight, you're going to have some area of polygons that we want you to find, and there's a a Delta Math that will help you do that. What I'd like to do now is return your tests and then give you the next 5 minutes to take a look at your tests, to ask me questions on what you don't understand, or get started on your homework. Sound okay? Say yes?